Hello, everyone, and welcome to the second part of section 6.7. Like I said, this physical application section was a little bit longer than I anticipated, mainly because there's a lot of background in the physics side of things. So applying that background to these problems, it's a little bit tougher to like rearrange all the formulas and stuff like that. There's one more kind of problem we haven't really discussed yet. Before in the last section, we talked about work required to like move a certain object or a body of water outside of its setting, and talking about slicing all those parts of the picture in order to take an integral. We have one more kind of problem, and it's more related to the force side of things. And I'm going to move on to that in here. So for force, again, force is equal to ma, but there's another part of force that we haven't talked about yet, and that's regarded to pressure. And pressure is the force exerted on a 2D surface. So really, it's a force per area. So in general, you can look at it in these two types of formulas here. Force is pressure times area, so P times an A, or you can look at it if we divide an area on both sides. Pressure is going to be force per area, so force divided by your area plate that you were looking at. And this has a really nice application in the examples regarding determining pressure or force on the face of a water dam. Very intuitive situation is that we're trying to create a body of water, and we want to make sure the dam we're creating is of a certain strength that can hold all the water that's going to be pushing against it. And we can do calculus to figure this out. Um, we probably will use a couple of the formulas from the prior section as well, but I'll repeat them as they come in. I'm trying to make this a little bit shorter because I know these videos are a little long here. So let's see how this looks here. So in the prior section, we saw that for ideal shapes, where there's just a constant force through on everything, we have F equals ma, which is just like where the magic starts, right? And in a prior class or prior section, we showed that mass is equal to density times volume. And volume we can break apart even further to be area times a depth, or area times a height, right? So if we have an ideal shape like a square to where there's nothing really varying or anything like that, the volume of this area would be the bottom base times a height. So bottom base times the height. So we can say this is the area of a face. We'll say the bottom face currently, and this is the depth of the face. So even if it wasn't the face on the bottom of the pool or of like a lake or something like that, if you just had a plate here on the bottom, the area of that plate and the depth that plate is at is going to determine the pressure on that plate too. Um, so if you have that pressure is equal to force times area, and we manipulated all these equations to get that force is equal to density times area times height, or times a depth times gravity, because we changed acceleration to gravity in this natural in real world situation. We have that pressure is just equal to that stuff divided by area. So pressure is equal to the density times the depth of that in that pressure, depth of that in the situation, and gravity, which the density of the water and gravity are usually always known. Density of water is like 1,000 kilograms per meter squared or something like that, per meter cubed, and gravity is 9.8 meters per second squared. Okay, that is if we have ideal shapes. And I'll also say, well, actually, I have it all right here, so I'll just resize it again like this. So when we're talking about pressure, or specifically hydrostatic pressure, it has the same magnitude in all directions, including on different faces of the dam. So in the situation we were talking about before, volume was found by looking at the area of the bottom times the height, and we found a certain pressure on this bottom face here. But since we have hydrostatic pressure, and hydrostatic pressure has the same magnitude in all directions, that means in different faces of the dam as well. So if I looked at this area here, or maybe a strip on the bottom here, like so, the pressure on that strip of this face that's on like the front of the dam, which is really what we're talking about, right? When we're doing a dam problem, we build a vertical dam to hold the water. So we wanted the pressure hitting the side of the dam. This pressure is going to be the same as the pressure on the bottom of the water as well, because it's all hydrostatic and all the same. So for not ideal shapes, again, we're going to have different forms of area depending on where we look at this wonky side of a dam. But at each slice of this dam, the pressure along that slice is going to be the same at that exact depth. So we have a bunch of different slices of different areas. If we make those slices really, really small, we add up all those slices together, limit it to infinity, we'll end up getting the integral that we're wanting to do. So we can do some calculus here. So when we look at the force on a kth slice in these non-ideal shapes, force again is pressure times area. Pressure is determined by the density of the water, which we already know, gravity, which is always constant, and the depth along that shape. And area means area of the strip we are looking at, which is usually a length times a width. We would have some length and we would have some width here like that. So the length of a kth strip is in general some change of y we are doing. And the width is something that's going to vary if we don't have an ideal shape. So I'm going to leave width as a function of some y star, where y star would be something like that for the kth slice, just like some arbitrary point chosen within that interval here. And h is the depth of that y star as well. So it would be whatever it is the distance to the top minus that y star to get to the bottom. So combining that all together, if this is along a kth slice, adding all those kth slices together throughout the entire interval of the dam gives us that force is equal to the integral from the bottom of the dam to the top of the dam of your density of the water or the liquid we're looking at times gravity times some width function times some depth function dy. So this is the width of each slice, and this is the depth of each slice. And that's really the last formula that we're going to be using. It's in a very neat, here, maybe I'll do this in yellow so that it's easier to see the green writing. It's written in a neat way to where now it's just like, okay, find the width of the slice, find the depth of the slice, plug it in, and let's go, you know? So let's look at this in an example here. Hydrostatic force and pressure. The following figure shows the shape and dimensions of a small dam. Assuming the water level is at the top of the dam, so let's color this in blue here. Assuming the water level is at the top of the dam, find the total force on the face of the dam, which is the exact situation we were starting with here, which means we're going to be using exactly this formula here. The bottom of the dam starts at 0. If we like create an origin right here, the top of the dam will be 30. We have a density of water, we have a gravity, we need a width function, and we need a height function, dy. And we're doing y's in this case. Now, the way we find the width function is choose some y. That's going to be at like some slice, right? The width of y is going to be this length here at that point. Now, that looks like kind of tough to find because we don't really have just like a formula. Maybe if we found out what like the slope of this was and the slope of this was, we could figure that out and stuff like that. But there's a more geometric way to figure this out. And that's if I have my lines be a little more straight here. Imagine this is a straight line. The way we figure this out, and that's actually a callback to the star problem in the last video, because this is how you would figure out a similar thing with that question I asked. The way we find the width here is through similar triangles. Is found through similar triangles. So I have a large triangle here that is 20 meters on its base and then 30 meters in its depth. And then I have a smaller triangle that has a base that is the width of y and a depth that is y. Now, I'm not trying to find what the width of y is as a number. My width of y is going to be in terms of y because it's changing as my depth changes as well. So that's going to be as expected. But since these are similar triangles, which means they share some angles, they all have the same angles and stuff like that, which means they're all proportionally the same. Proportion is the key word here. That means if you look at the proportion of like a base and its depth for one triangle, that needs to equal the proportion of a base and the depth of the other triangle. Rearranging this means the width of y is equal to 2/3, not w, y here. So in this problem, finding the width of y wasn't that bad. That's usually the tough part of these problems, but if you know what you're looking for, it shouldn't be the toughest thing in the world. Sometimes you'll have even a more wonky dam, something like that. So your width of y might be more dependent on how we define the side here. So say if this was like a parabola, and we're looking for the width of y, and this is a parabola determined by like, let's say like x squared or something like that. That means if you're looking sideways, this parabola will look like a square root of y on this side and a negative square root of y on this side. So the width is going to be double whatever square root of y is at this depth. So width of y in this case would be 2 square root of y. So if you have the function of your sides here, you can figure out what the width is as well by doing some algebraic manipulations. But here we were able to figure it out with similar triangles, which is the way this problem wanted us to do it. So also, we have the width of y, h of y, which is the depth at y, that's equal to, this whole depth is 30, and then I subtract a y amount to get to my length, or get to my depth spot, so 30 minus y. That gives us that force is equal to 0 to 30 of rho times g times 2/3 y for width of y times height or depth of y, which is 30 minus y. And then we have that dy tacked at the end. Since we know these constants are 1,000 and 9.8, since we're working with water here, water is always 1,000 kilograms per metric of volume, or per meter squared. Ooh, I don't want to do that. Let me delete that real quick. I think we're almost done here, so we'll just add another page here. So this is going to be 9,800 times 2/3 times the integral from 0 to 30 of y squared, or 30y minus y squared, y. And these numbers on the outside are a little annoying, but we can just plug that into a calculator later to get 15y squared minus y cubed over 3 when we integrate from 0 to 30. And I would encourage you to plug this in a calculator on your own, but if you plug it all in, evaluate 30, plug in the numbers and expand, you should get 1176000. So 1,176,000 newtons of force on that wall. So the flow of this problem, before I end it here, is the way to find the force on a dam is through this formula here. It was derived the page prior, but if you started with this formula, that's going to be totally fine for this for problems like this. And the trick is to find what your width is at each slice and what your depth is at each slice. Depth is going to be a little easier because you just have like a certain depth that you're looking at. So usually you're subtracting the entire thing by like a y, or you might be a little different because maybe we have a little bit higher of a depth if the water's not totally full, stuff like that. The width is going to be a little tougher because it's going to depend on what these sides are. And that is it. Thank you for watching.